Welcome back, scholars. In this video, we move on to question 4 of the BBIT300, also cross-listed as BIT3201A Data Mining and Data Warehousing paper, sat in April 2019. Question 4 is worth 20 marks and it is one of the optional questions, so you only attempt it alongside question 1 and one other. It is entirely about data preprocessing. Why we preprocess, how we fill in missing values, dimension reduction, and a work dataset where you decide what to clean, integrate, transform, and reduce before feeding it to a decision tree. By the end, you'll be able to explain the significance of preprocessing, list 3 imputation methods, describe dimension reduction, and walk through the 4 preparation tasks on a real table. Let's begin. Here is the roadmap. Question 4 has 4 parts, 20 marks in total. Part A, 2 marks, asks you to briefly explain the significance of data preprocessing in a data mining process. Part B, 6 marks, asks for any 3 methods that can be used to fill in missing values during preprocessing. Part C, 4 marks, asks you to describe dimension reduction as a technique of data reduction. And Part D, 8 marks, the big one, gives you a small table of student records and asks, for each of 4 tasks, what you would need to do before using a decision tree learning algorithm. Those tasks are data cleaning, data integration, data transformation, and data reduction. Parts B and D carry 14 of the 20 marks between them, so they are where the bulk of your writing time should go. Part A, 2 marks, briefly explain the significance of data preprocessing. Real-world data is messy. It is collected from many sources in many formats, often with errors, gaps, duplicates, and inconsistencies. If you feed that raw data straight into a mining algorithm, you get the classic garbage in, garbage out. The model simply learns the noise. Preprocessing is the stage where we clean, integrate, transform, and reduce the data so that the mining algorithm receives high-quality, consistent input. And here is the key insight the examiners want. Data scientists spend roughly 80% of their time on preprocessing, and the quality of preprocessing directly determines the accuracy, the speed, and the reliability of the model that follows. Without it, classifiers overfit, clusters blur, and rules mislead. In short, preprocessing turns raw data into trustworthy, analysis-ready data, and it is the single biggest lever on result quality. Part B, 6 marks, any 3 methods to fill in missing values. The question asks for 3, so let's take them 2 at a time. Method 1, ignore or drop the tuple. If a row has only a few missing values, or if the missing values cannot reasonably be filled, you simply delete the whole record. It is fast and avoids fabricating data, but it wastes information and can bias the dataset if the missingness is not random. Method 2, fill with a global constant. You replace every missing value with a single placeholder label, such as the word unknown for a category, or a special number like -999 for a numeric field. The algorithm then treats unknown as its own category. It is simple and works for any attribute, but the algorithm may mistakenly treat that constant as a meaningful value, so you have introduced a signal that is not really there. Method 3, fill with the attribute's mean or with the most probable value. For a numeric attribute, you replace the missing entry with the average of all the known values, so a missing exam score becomes the class average. For a categorical attribute, you replace it with the mode, the most frequent category. A more sophisticated variant uses regression or a decision tree on the other attributes to predict the most likely value for the missing one. This is statistically grounded and keeps the dataset complete, but it can dampen variance. Every filled value sits at the center, so the data looks smoother and less varied than it really is, which can mask genuine patterns. So there are your 3 methods. Drop the tuple, fill with a global constant, or fill with a mean or most probable value. Each trades off simplicity against statistical fidelity. The examiners give a mark for each, +1 for naming the trade-off. Part C, 4 marks, describe dimension reduction as a technique of data reduction. A dataset with hundreds of attributes is said to be high-dimensional, and that creates 2 problems. Storage and compute grow rapidly, and many of those attributes are redundant or irrelevant. They add noise without adding signal. Dimension reduction is the process of reducing the number of random variables or attributes under consideration while preserving the meaningful information. There are 2 main strategies. The first is feature selection. Pick a smaller subset of the original attributes and discard the rest. Techniques include removing low-variance attributes, correlation analysis, and the chi-square test. The second is feature extraction. Combine the original attributes into a smaller set of new derived features that capture most of the variance. The classic technique here is principal component analysis, which projects the data onto a few orthogonal axes of greatest variance. The benefit is huge. Smaller, faster models that are less prone to overfitting. The curse of dimensionality is broken. Now Part D, 8 marks, the work dataset. Here is the table. 5 student records with 7 columns: ID, major, average project score, average exam score, whether they did a co-op, whether they are employed, and their salary. Look closely and you'll see the mess straight away. Student 2, the history major, has a missing project score and a missing salary, both shown as question marks. The salary column mixes real numbers with a 0 for student 4, who is unemployed. Major is text, the scores are numeric, the Y and N flags are categorical, and the ID column is just a row label that carries no real signal. The question asks, for each of 4 tasks, what, if anything, you would do to this dataset before feeding it to a decision tree learning algorithm. The 4 tasks are data cleaning, data integration, data transformation, and data reduction. On the next 2 slides, we'll take them 2 at a time and pin each one to a concrete action on this exact table. Task 1, data cleaning. This is where you fix the messy cells. The 2 question marks in student 2's record are missing values, so you apply one of the methods from part B. For the project score, fill with the mean of the other students' project scores. For the salary, you might either drop the tuple or fill with the mean salary, but never with 0 because 0 means unemployed here. Next, the salary of 0 for student 4 is not an error. It correctly encodes an unemployed graduate, but you should make sure the algorithm treats it as a meaningful value, not as missing. You'd also check for outliers and obvious typos in the score columns and confirm the ID column has no duplicates. Task 2, data integration. This table is already a single source, so there is no actual merging to do, and the honest exam answer is to say so. But you should still describe what integration would involve if a second table existed. Resolving schema conflicts, removing duplicate records that refer to the same student, and detecting redundancies where 2 columns carry the same information. Naming that there is nothing to integrate is itself worth the mark. Task 3, data transformation. Decision trees handle categories fine, but scores and salary sit on very different scales, and some algorithms are sensitive to that. The common transformations are 3. First, smoothing, reduce noise in the numeric scores. Second, normalization, rescale each numeric column. For example, min-max normalization to put every score between 0 and 1, so project score, exam score, and salary do not dominate each other. Third, generalization, replace low-level raw values with higher-level concepts. For example, binning the salary into low, medium, and high, or grouping majors into broader categories. Task 4, data reduction. The clearest action here is dimension reduction by dropping the ID column. It is a unique row label with no predictive value, so it adds nothing but noise. Beyond that, with only 5 rows and 7 columns, the dataset is already small, so aggressive reduction is not needed. But you would describe what you could do. Feature selection to drop weak predictors, principal component analysis to compress the numeric attributes, or numerosity reduction to represent the data more compactly. The exam answer is to drop ID and to show you know when to stop. Let's lock in the takeaways. First, the significance of pre-processing. Real data is messy, garbage in means garbage out, and pre-processing, cleaning, integration, transformation, and reduction is what turns raw data into trustworthy, analysis-ready input. Second, 3 ways to fill missing values. Drop the tuple, fill with a global constant like unknown, or fill with the mean for numbers and the mode for categories. Third, dimension reduction cuts the number of attributes while keeping the information, either by feature selection, picking a subset of the originals, or by feature extraction like principal component analysis, building new derived features. Fourth, for the work dataset, 4 tasks map to 4 actions. Cleaning fixes the question marks and the 0 salary. Integration is mostly a nothing to do here, but you name the merge steps. Transformation smooths, normalizes, and generalizes the values, and reduction drops the ID column and stops there because the table is already small. Memorize these 4 points and question 4 is fully covered. In the next video, we'll tackle question 5. Until then, keep revising.